Seismic monitors flashed urgent warnings across California's scientific community, but what they traced beneath the waves was unprecedented. Verified footage now reveals the sudden collapse of the ocean floor, with massive sinkholes opening along the Pacific Shelf. This event has frontline neighborhoods fearing for their homes, and researchers are scrambling to unravel what triggered such a destructive shift. Is this just the start of something much bigger lurking under California's coast, or the warning sign that scientists have dreaded for years? The real question is, what does the data prove, and can anyone truly verify what happened next? A digital fingerprint sits inside every video file, hidden data that can reveal exactly when and where a recording was made. For the two viral clips at the center of this investigation, analysts began with the raw files themselves, using EXIF tool to extract embedded timestamps and device signatures. The first file, labeled NT49GJ8L1UU, listed a creation time of 3:14 and 27 seconds UTC, with a GPS tag fixed at 34.0037 degrees north, 120.4121 degrees west. The second file, NJYSD-DTBLV6C, carried a time code of 3:16 and 4 seconds UTC, 97 seconds later, and mapped to a location less than half a nautical mile from the first. Both coordinates plot directly onto the Santa Barbara Channel, a region known for active faults and steep underwater slopes. Scrubbing through the footage frame by frame, investigators matched the overlay panel in the lower left, a vessel automatic identification system readout, against public maritime logs. At 3:15 UTC, the research vessel Horizon appeared in the area, its automated position log confirming movement along a southwest track at 2.3 knots. The vessel's heading, speed, and timestamp all align with the embedded metadata from both video files, ruling out after-the-fact editing or relocation. The time sequence is tight enough to suggest a continuous observation, not a composite or staged event. To verify the authenticity of the location, analysts compared visible bathymetric features in the footage, distinctive ridges and cable markers, against charts from the National Oceanic and Atmospheric Administration. Each feature in the video mapped precisely to known underwater structures, down to a margin of error of less than 30 meters. Even the light flicker patterns, shaped by the vessel's track and water clarity, corresponded to the ship's logged heading and the time of day, as confirmed by sunrise data for the Channel Islands sector. Matching UTC time codes, GPS coordinates, and vessel movement logs eliminates nearly all doubt about the physical provenance of these recordings. The chain of evidence now ties raw video files, embedded device stamps, and live ship tracking into a single verifiable timeline. With the digital trail established, the next step is assembling the interview packet, frame grabs, metadata overlays, and mapped coordinates ready for expert analysis. Each detail, from the automatic identification system overlay to the EXYF tags, stands as a piece of forensic evidence, linking the shocking images to a real-world event pinpointed by both time and place. 6 institutions received the first wave of data packets: Scripps Institution of Oceanography, MBARI, NOAA's Pacific Marine Environmental Laboratory, the USGS Coastal and Marine Geology Program, California Geological Survey, and Ventura County's Office of Emergency Services. Each packet included a curated set of frame grabs from the original video files, with embedded coordinated universal time codes and coordinate overlays. High-resolution bathymetric tiles extracted from the NOAA multi-beam archive were clipped to cover the precise area of the Santa Barbara Channel, flagged by the GPS metadata. Sensor IDs from the vessel's remotely operated vehicle, serial VCAL25 as registered in the Horizon's equipment log, were cross-referenced against the ship's manifest and included as a separate appendix. The packet also contained a side-by-side comparison of the video visible cable markers with the latest USGS submarine infrastructure map, allowing specialists to link observed features to real-world installations. A log of vessel positions drawn from the AIS system and annotated for the 0314 to 0317 coordinated universal time window accompanied the footage, ensuring that each expert could trace the movement of the research vessel in real time. For context, investigators added a digital elevation model of the seafloor, highlighting known ridges and slope breaks within a 500-meter radius of the event coordinates. To ensure clarity, each packet was formatted with a consensus line request, a single-sentence summary from the recipient stating whether the evidence supports, contradicts, or remains inconclusive regarding a sudden seafloor collapse at the mapped site. This requirement, standard in multi-institutional investigations, helps distill complex technical feedback into a clear public message. A contact roster listed the lead analyst at each agency with direct lines for follow-up questions and a standing invitation to participate in on-record interviews. All materials were encrypted and dispatched via secure file transfer, with delivery receipts logged for chain of custody. Within hours, confirmation messages began arriving from the Scripps and MBARI teams, acknowledging receipt and flagging their review timelines. As the data packets circulated, the process shifted from digital verification to expert interpretation, setting the stage for a coordinated review of the evidence by California's top marine geohazard authorities. The first signals arrived at 03:14:31 UTC, when a subtle tremor registered on the Caltech ANSS seismic array just offshore from the Santa Barbara Channel. This microseismic blip, lasting under 4 seconds, fell below the threshold for public earthquake alerts, but its timing lined up precisely with the vessel's GPS-logged position. Less than 20 seconds later, a sharp acoustic spike cut through the ocean bottom hydrophone network managed by Scripps. The hydrophone at node SB07, anchored at 34.004 degrees north, 120.413 degrees west, recorded a broadband burst, peaking at 2.1 kHz, lasting just over half a second. Analysts flagged the event for its sudden onset and amplitude, characteristics more typical of rapid sediment movement than tectonic fault slip. At 03:15:02, the research vessel's ROV, serial VCAL-25, transmitted a live depth reading from its altimeter. The display, logging a stable 187 meters for the previous hour, now showed a sudden drop to 231 meters. The depth change, a loss of 44 meters in less than 60 seconds, triggered an automated alert in the ship's monitoring software. Crew logs confirmed that the ROV had not moved laterally, ruling out a navigational error or descent into a canyon. Instead, the bathymetry feed revealed a new depression, an abrupt void where the seafloor had previously formed a gentle slope. By 03:15:17, a secondary acoustic disturbance echoed through the hydrophone array, this time with a lower frequency signature and longer duration. MBARI's real-time data relay captured the signal, noting it spread across multiple nodes within a 700-meter radius. This pattern suggested a cascading collapse rather than a single-point failure. Simultaneously, the vessel's downward-facing multi-beam sonar began returning erratic returns, with bottom loss and water column scatter consistent with a plume of suspended sediment. The sonar logs stored in the ship's event archive show a sharp transition from clear seafloor imaging to high turbidity interference, beginning at 03:15:21 and persisting for nearly 3 minutes. At 03:16:04, the second video file's timestamp aligned with a depth sensor reading of 234 meters, another 3-meter loss since the initial collapse. The ROV's cameras, still streaming, captured billowing clouds of fine silt drifting upward from the depression's rim. Acoustic Doppler current profiler data transmitted to the vessel's bridge recorded a sudden upwelling, with velocities peaking at 0.7 meters per second. This updraft, lasting just under a minute, marked the final phase of the disturbance. Throughout the sequence, each instrument, seismic, acoustic, bathymetric, registered the event in close succession, locking a clear chronology. The onset began with a microseismic tremor, followed by a sharp acoustic spike, then a rapid loss of seafloor depth, and finally a sustained period of sediment plume and water movement. These signals, ordered minute by minute, provided the foundation for reconstructing the event's full timeline and identifying the critical gaps that would shape the next stage of analysis. Satellite coverage across the Santa Barbara Channel is anything but continuous. The nearest Sentinel-1 pass, logged at 2:49 Coordinated Universal Time, captured the sector nearly half an hour before the first seismic blip. The next available radar sweep did not arrive until 4:21 Coordinated Universal Time, well after the collapse sequence had played out. In between, there is a blackout, no real-time satellite imaging, no surface disturbance visible from orbit, and no automated alert triggered by the usual marine hazard algorithms. This gap in overhead surveillance leaves a critical blind spot at the exact moment the ocean floor changed. On the seafloor itself, the absence of a deployed ROV during the initial microseismic activity adds another layer of uncertainty. The vessel's submersible, VCAL-25, was powered up and logging depth by 3:15 Coordinated Universal Time, but no instrument was positioned on the bottom to record pre-event sediment conditions or gas flux. Without a stationary sensor at the collapse site, there is no direct evidence of a methane burst, no water column chemistry profile, and no baseline for sediment stability. The only available data come from the ROV altimeter and the vessel's downward-facing sonar, reactive, not predictive, and started recording after the event was already underway. The microburst detected by the Caltech seismic array at 3:14:31 Coordinated Universal Time remains unverified as a trigger. No corroborating hydrophone data from before this moment, and no ground truth samples from the site leave its cause open to interpretation. Was it a small tectonic slip, a sudden gas release, or an unrelated background tremor? The lack of high-frequency hydrophone logs for the preceding minutes prevents a clear answer. Even the acoustic spike at node SB07, while dramatic, cannot be directly linked to a specific mechanism without supporting chemical or physical evidence from the collapse zone. Further complicating the timeline, the bathymetric model in the expert packets is based on pre-collapse National Oceanic and Atmospheric Administration data and post-collapse ROV readings. There is no high-resolution multi-beam sweep taken in the minutes or hours before the depression formed. Any calculation of lost sediment volume, failure geometry, or scar depth must rely on interpolated surfaces and best guess estimates, not direct measurement. The missing interval between the last mapped slope and the sudden drop is where the most critical forensic evidence should lie. These timeline gaps are not just technical oversights, they define the limits of what can be proven about the collapse. Without satellite imagery at the moment of failure, without ROV sensors on the seafloor beforehand, and without verified seismic triggers, the chain of causation remains incomplete. For scientists, these uncertainties set the requirements for any future mechanism testing. Denser satellite revisit schedules, continuous hydrophone and ROV monitoring, and rapid response sampling protocols. Until those gaps are filled, every theory about what triggered the collapse remains provisional, shaped as much by what is missing as by what has been recorded. Methane gas trapped beneath the seafloor has long been suspected as a silent force shaping the ocean bottom. When pressure or temperature changes destabilize these buried hydrates, methane can escape upward, carving out pockmarks and, in rare cases, triggering collapse. The Santa Barbara Channel, like much of California's offshore margin, is riddled with these pockmarks, circular depressions that dot the seabed for miles. Some reach more than 100 meters across, their origins linked to ancient gas blowouts. To test whether such a mechanism could explain the recent collapse, analysts turn to the acoustic record. Methane bubbles released from the seafloor generate a distinct signature. As they rise, they scatter sound waves, producing a frequency band often centered between 500 Hz and 5 kHz. Hydrophone arrays, like those deployed by Scripps and MBARI, are tuned to pick up these bubble plumes, translating the chaos of underwater gas escape into measurable data. The acoustic spike recorded at node SB07 stood out for its sharp onset and intensity, but its frequency profile told a different story. Instead of the broad, fluttering spectrum characteristic of a methane blowout, the signal peaked narrowly at 2.1 kHz and faded in under a second. Analysts compared this pattern to archived gas seep events from the Coal Oil Point field, just up the coast. In those cases, the hydrophones captured a series of overlapping chirps, each bubble cluster rising through the water column, modulating the acoustic environment for several seconds or more. The Santa Barbara Channel event lacked this signature. There were no trailing harmonics, no evidence of sustained gas release. Instead, the hydrophone record resembled a sudden mechanical disturbance, more akin to sediment collapse than to a plume of escaping methane. Geochemists then examined the available water column data. In methane-driven events, dissolved gas concentrations spike rapidly above the collapse zone, often accompanied by visible bubbles in ROV footage. But the altimeter and sonar logs from the ROV on the research vessel RV Horizon showed only suspended sediment, fine silt and debris, not gas bubbles. The water column remained acoustically opaque, with no sign of the telltale bubble trails that would point to a methane blowout. Even the sediment plume captured by the downward-facing sonar drifted slowly upward, lacking the violent upwelling seen in known gas eruption sites. The pockmark indicator, a clustered field of circular depressions, is a classic marker of past methane release. Yet the new depression mapped after the collapse did not match this geometry. Its margins were irregular, the scar elongated downslope, and the volume of displaced material exceeded what is typically associated with single-point gas blowouts. When the expert panel compared the Santa Barbara Channel event to documented methane eruptions in the North Sea and Gulf of Mexico, the differences became more pronounced. Those blowouts left behind neat rimmed craters, often with residual gas seeps nearby. Here, the evidence pointed elsewhere. The verdict from the geochemical analysts was measured but clear. While methane blowouts have shaped parts of California's seafloor, the acoustic and physical signatures from this collapse do not fit the established pattern. The absence of a broad bubble frequency band, the lack of water column gas anomalies, and the irregular scar geometry all argue against a gas-driven event. The search for a mechanism continues, but for now, the methane hypothesis stands on uncertain ground. Marine geologists began with the raw geometry of the collapsed scar, plotting its length, width, and depth against established models of submarine landslides. The depression stretched more than 320 meters downslope, with a maximum width near 90 meters and a measured depth from rim to floor of just over 44 meters. The shape was irregular, its margins jagged, trailing off into a runout zone of scattered debris. To test whether rapid slope failure could account for these dimensions, researchers reconstructed the pre-event seafloor using archived NOAA bathymetric grids and interpolated the missing surface. By subtracting the post-collapse ROV altimeter profile from the estimated original slope, they calculated a displaced sediment volume of approximately 560,000 cubic meters, roughly equivalent to 225 Olympic swimming pools. The next step was to compare this geometry to known landslide scars in the Santa Barbara Channel and similar continental margins. Most local submarine slides are smaller, often less than 100 meters across, with shallow headwalls and limited runout. The new scar's elongated footprint and steep upper wall, measured at nearly 28 degrees, suggested a higher energy event. In landslide mechanics, slope angle and sediment cohesion are critical. Slope stability models applied here use the balance between downslope gravitational force and the resisting strength of seafloor sediments. When the driving force exceeds the shear strength of the sediment, failure becomes inevitable. Laboratory tests on cores from this region typically yield undrained shear strength values between 12 and 25 kilopascals, depending on depth and consolidation. At a slope angle above 25 degrees, even minor disturbances, such as small seismic shaking or rapid sediment loading, can tip the balance. Modeling the failure, geologists input the measured slope, estimated sediment density, and the calculated volume into a finite element simulation. The result is that the observed scar dimensions and rapid depth loss align closely with a scenario of translational slope failure. The headwall steepness and the elongated downslope track point to a sudden rather than gradual movement, likely a block of sediment detaching and sliding as a coherent mass before breaking up and dispersing. The absence of a circular crater or uplifted rim further supports a landslide mechanism over a gas blowout. Volume estimates compared to local stability limits also reveal the event's scale. For a failure of this size to occur, the sediment mass must have lost enough internal strength to overcome both friction and cohesion. This could result from excess pore water pressure, progressive oversteepening, or even subtle tectonic movement along a buried fault. While the exact trigger remains uncertain, the geometry and mechanics of the scar are consistent with a rapid slope failure, not a slow creep or isolated gas eruption. The data now point toward a landslide origin, setting up the next phase of analysis, whether fault activity or broader tectonic stress played a role in the collapse. Geologists working the Santa Barbara Channel overlay regional fault maps onto the collapse coordinates, tracing a web of fractures running parallel and oblique to the coast. The channel sits at the intersection of several active offshore faults, among them the Hosgri, Red Mountain, and Santa Cruz Catalina Ridge systems. These faults, though smaller than the San Andreas, accommodate significant stress transferred from the continent's relentless tectonic grind. Using slip deficit data, analysts calculate the rate at which strain accumulates along these buried fractures. For the Central Channel, recent GPS and seafloor geodetic surveys report slip deficits of 2 to 4 millimeters per year, a pace that quietly loads energy into the system over decades. To test whether a sudden stress release along one of these faults could have triggered the observed collapse, scientists turned to models of stress transfer. The minimum radius for a slip event to influence nearby faults or slope stability is set by both the size of the rupture and the mechanical properties of the surrounding crust. In Southern California, studies show that a moderate offshore slip, on the order of magnitude mapped here, can alter stress fields within a zone up to 50 kilometers from the epicenter. This threshold, derived from earthquake aftershock patterns and laboratory rock mechanics, defines the plausible reach for a chain reaction. Beyond this radius, the energy dissipates, and the risk of immediate triggering drops sharply. Analysts run simulations using the map geometry of the collapse scar and the known fault traces. The models show that if a slip occurred within the 50-kilometer stress transfer radius, it could feasibly destabilize oversteepened slopes or preconditioned sediment blocks nearby. However, the data from the Santa Barbara Channel event point to a localized failure, with no evidence of synchronous slip or triggered activity on adjacent faults. Seismic records from the Caltech array do not show a cascade of aftershocks or secondary tremors, and no offshore faults in the immediate vicinity display measurable surface rupture or vertical offset in the aftermath. The broader narrative of a Pacific-wide chain reaction, the so-called Ring of Fire scenario, faces even greater physical limits. The Pacific Rim's tectonic arcs, while connected by the movement of plates, are separated by thousands of kilometers and vast stretches of oceanic crust. Stress transfer across such distances is not supported by established geophysical models. While regional clustering of earthquakes can occur, especially after major subduction events, a single submarine landslide or fault slip in California is not sufficient to set off a domino effect around the Pacific. The Ring of Fire remains a framework for understanding global tectonics, but the evidence here restricts any potential chain reaction to the local fault network. The verdict from tectonic analysts is measured. Stress transfer from offshore slip can influence nearby slopes and faults, but the reach is sharply bounded. The 50-kilometer radius sets a practical limit for hazard scaling, and the absence of a multi-fault response in the Santa Barbara Channel event argues against a broader chain reaction. The focus now shifts to local hazard assessment, where even a single slip or collapse can have outsized consequences for coastal communities perched above the shifting seafloor. Tsunami risk along California's coast is often measured against a handful of historic underwater landslides that left a mark far beyond their local waters. The 1929 Grand Banks event off Newfoundland, for example, released nearly 200 cubic kilometers of sediment in a matter of minutes. That collapse sent a wall of water racing across the Atlantic, with waves reaching up to 13 meters along the Canadian coast and snapping transatlantic telegraph cables in sequence. In Papua New Guinea in 1998, a much smaller slide, about 4 cubic kilometers, still managed to generate a tsunami with run-ups as high as 15 meters, devastating coastal villages in less than 10 minutes. Even the 2018 Anak Krakatau collapse, triggered by a volcanic flank failure, moved just 0.27 cubic kilometers of material, yet produced local waves up to 85 meters high. To estimate the odds of a California submarine landslide producing a similar disaster, scientists apply scaling laws that relate the volume and speed of underwater collapse to the height and reach of the resulting tsunami. The Santa Barbara Channel event, reconstructed from vessel and ROV data, displaced about 560,000 cubic meters of sediment, roughly 0.00056 cubic kilometers. This is several orders of magnitude smaller than the slides that triggered the Grand Banks or Papua New Guinea tsunamis. The geometry matters too. Those historic waves were generated by sudden, rapid movement of vast sediment blocks, often along very steep slopes, and in some cases aided by earthquake shaking. The mechanics of tsunami generation require both speed and scale. A slow slump, even if large, tends to dissipate its energy before it can push enough water to generate a hazardous wave. By contrast, a compact high-velocity collapse, like the Grand Banks or Anak Krakatau, can transfer massive energy into the water column in seconds. In California's offshore margin, most mapped submarine slides are smaller and slower, with few showing the steep headwalls or rapid runout needed for major tsunami production. The Santa Barbara Channel scar, while dramatic in its local context, does not approach the critical volume or failure speed seen in benchmark disasters. Probability brackets for tsunami generation off California reflect these physical constraints. NOAA and USGS hazard models indicate that while submarine landslides can and do occur along the state's underwater slopes, the odds of a locally generated life-threatening tsunami remain low compared to regions like Southeast Asia or the North Atlantic. Still, the presence of steep slopes, active faults, and thick sediment packages means the risk is not zero. Ongoing monitoring focuses on detecting the rare combination of volume, slope, and trigger, such as a strong earthquake or rapid sediment overload, that could push a future event into the dangerous range. For now, the evidence places California's recent collapse well below the threshold for a catastrophic tsunami, but the geological record reminds us that the ocean floor is never truly at rest. Bluff-top homes in coastal California have always balanced on a line between ocean views and geological risk. In November 2025, that line moved dramatically for residents of Rancho Palos Verdes. A 400-foot section of the coastal bluff gave way overnight, sending earth, vegetation, and a section of trail tumbling into the Pacific. Emergency crews cordoned off the area, and structural engineers inspected nearby homes for cracks and shifting foundations. While no one was injured, the incident forced dozens of families to evacuate, some indefinitely. The collapse was not triggered by a single storm or earthquake, but by the slow, relentless process of marine erosion, gravity, and the gradual weakening of the bluff's base. Subsidence data from the region paints a worrying picture. Satellite measurements show that certain coastal neighborhoods are sinking by more than 1 inch each year. This downward movement compounds the threat posed by rising sea levels, making low-lying properties even more vulnerable to flooding and sudden ground loss. In the Bay Area, Ventura, and Monterey, similar patterns are emerging: cliffs retreating, homes inching closer to the edge, and infrastructure under increasing strain. For residents, the risks are not abstract. County emergency managers have ramped up community alert systems in recent years, issuing targeted warnings when heavy rainfall, seismic tremors, or visible bluff cracking suggest an increased danger of collapse. These alerts, delivered by text, mobile app, and local radio, are often the first sign that evacuation may be necessary. In some neighborhoods, evacuation drills have become a routine part of life, with routes mapped and emergency kits packed in advance. Preparedness now extends beyond individual households. Local governments have established rapid assessment teams to inspect damage after landslides or bluff failures. Some cities have begun reinforcing vulnerable stretches of coast with seawalls or managed retreat plans, relocating critical infrastructure away from the most unstable zones. Public works departments monitor ground movement using GPS and INSAR data, while engineers assess the stability of roads, pipelines, and utility corridors that run close to the bluffs. The experience in Rancho Palos Verdes stands as a warning and a lesson. As the pace of coastal change accelerates, communities on the front line are adapting, sometimes in small practical ways, sometimes through sweeping changes in land use and emergency planning. The science of seafloor collapse and landslide risk may play out offshore, but its consequences are felt most acutely by those whose homes' livelihoods and daily routines depend on a stable coastline. California's shifting ocean floor isn't just a scientific anomaly, it's a warning. Today, over 27 million Californians live near the coast, their safety dependent on what happens beneath the waves. As the Pacific Ring of Fire grows more unpredictable, the line between land and sea blurs. Nature's next move could redraw California's very map and shape the fate of every community along its edge. Tonight, the unthinkable is happening off California. New land is rising overnight from the ocean floor, while entire neighborhoods are collapsing into the sea. And the seafloor is rising off California, and scientists are baffled. Over 130 homes have already been lost, and what's truly alarming is nobody expected a simple 1956 road project to unleash this geological chain reaction. Could it get even worse? To understand how human ambition triggered a natural disaster where sinking land creates uplift, we have to start at the very moment physics turned upside down. Gravity, as most people know it, is supposed to pull everything down. But off the coast of California, something strange is happening. Instead of sinking, the seafloor is pushing upward as if the laws of physics have been quietly rewritten beneath the waves. The puzzle begins with a vast slab of land perched on a hidden ramp deep below Rancho Palos Verdes. Instead of sitting flat, this ancient layer of shale dips gently toward the ocean, forming a natural incline that runs for hundreds of meters. Picture a massive block sliding slowly down a tilted ramp. It's not just moving forward, it's also being forced upward, like a lever prying open a stubborn lid. Each inch of horizontal slip translates into a fraction of vertical lift, all because of the geometry of the ramp beneath. The math behind it is surprisingly simple. The steeper the angle, the more upward force is generated for every bit of sideways movement. For the Portuguese bend slide, the ramp can tilt anywhere from 6 to 22 degrees. Even at the gentlest slope, the result is a subtle but unstoppable push that lifts the seafloor. This isn't a one-off event. The process unfolds every time rainwater seeps into the fractured earth, reducing friction along the slippery clay layer at the base. The landmass lurches forward, and the ramp beneath it acts like a giant crowbar, converting that motion into uplift. The effect is magnified where the ramp thickens or the angle steepens, creating hot spots where the ocean floor rises faster than anyone thought possible. Geologists call this the geological lever effect. It's a mechanical paradox. As land onshore collapses, the seabed offshore rises. The two movements are locked together, each feeding off the other. This coupling defies the intuition that what goes down must stay down. Instead, the Earth's own architecture turns collapse into creation, trading the loss of homes and roads for new land forming beneath the waves. The evidence is not just theoretical. Satellite radar and GPS measurements track the movement in real time, showing the ground surging forward and the seafloor bulging upward in response. Computer models and laboratory experiments confirm the same principle. When a massive slab of earth slides down an inclined plane, the ramp's slope determines how much of that motion becomes vertical lift. The process is efficient, relentless, and entirely governed by the physics of the underground ramp. This is the paradox at the heart of California's rising sea floor, a natural lever powered by gravity, geometry, and the hidden weakness of the rocks below. The land that falls away above is, quite literally, raising the ocean floor below. It's a mechanical puzzle that has left even the experts searching for answers, and it all began with a silent shift deep beneath the hills of Rancho Palos Verdes. In 1956, bulldozers rolled onto the quiet hillsides above Portuguese Bend, launching the Crenshaw Boulevard extension. What began as a routine infrastructure project would soon become a textbook case of unintended consequences. County engineers ordered the excavation of more than 1 million cubic yards of earth, slicing through ancient dormant landslide deposits that had rested undisturbed for thousands of years. The plan called for cutting into the hillside, rerouting drainage, and laying a new ribbon of asphalt to connect the growing suburbs. But beneath the surface, the ground was anything but stable. Construction crews encountered layers of bentonite-rich clay, a material notorious for its slipperiness when wet. Soil tests from the time revealed a friction angle of just 6 degrees, slicker than a wheelchair ramp. Despite warnings in county meeting minutes and the cautious voices of local geologists, the project pressed ahead. Drainage patterns were altered as culverts and channels redirected water runoff, funneling it into the very earth that had once held steady. The removal of stabilizing weight at the top of the slope, combined with the influx of water, set the stage for disaster. Within months of the road's completion, cracks began to snake across the pavement. Freshly graded slopes slumped and buckled. By the end of 1956, the ground was moving. The dormant landslide, estimated to have been still for at least 5,000 years, was now awake and hungry. Aerial photographs from the late 1950s show a patchwork of shifting earth and collapsing homes, each new slide tracing the path of the newly built road. The destruction moved fast. Over 130 houses were condemned or destroyed within just 18 months. Insurance claim records from the period document a relentless sequence of losses. Whole streets rendered uninhabitable, families forced to evacuate as their foundations twisted and walls split apart. Local headlines captured the chaos. Neighborhood slips into sea, 35 homes gone, while city council minutes declared disaster zones and authorized emergency closures. Residents watched as lawns buckled, utility lines snapped, and roads vanished into the earth. Each week brought new damage, the pace of destruction matching the slow, unstoppable creep of the hillside itself. Geotechnical reports commissioned in the aftermath left little doubt about the cause. The removal of stabilizing earth and the redirection of water by the Crenshaw Boulevard project had reawakened a prehistoric landslide, one that no amount of modern engineering could put back to sleep. Today, scientists and city planners cite Portuguese Bend as a cautionary tale, a stark reminder that even the best intentions can unleash forces far beyond human control. Beneath the surface of Rancho Palos Verdes, a thin layer of bentonite clay holds the key to the hillside's uncanny mobility. This clay, formed from ancient volcanic ash, has a unique property. When it gets wet, its friction drops to almost nothing. Laboratory tests show a friction angle of about 6 degrees, less resistance than a wheelchair ramp. On a dry day, the clay acts like a weak glue, holding the overlying rock in place. But after a heavy rain, water seeps down, saturating the bentonite and turning it into a natural lubricant. The result is a surface so slick that even gentle slopes can't hold back the mass above. Geotechnical specialists have measured these properties using core samples pulled from deep within the landslide zone. In controlled experiments, they found that a block of earth perched on a 6-degree slope of wet bentonite will start to move under its own weight, no extra force required. The clay's microscopic structure, tiny flat mineral sheets stacked together, traps water between layers, swelling and weakening the bonds that would normally keep the hillside stable. As pore pressure builds, the effective stress drops, and the entire hillside is free to glide. This slippery truth explains why the land above seems to defy gravity. The bentonite slip layer acts as a geological conveyor belt, set in motion by nothing more than rainfall and the relentless pull of gravity. It's not just the angle of the ramp that matters, but the chemistry and physics of the clay itself. An invisible hazard that turns solid ground into a moving platform whenever the conditions are right. Every morning in Rancho Palos Verdes, the ground beneath people's feet is somewhere new. Fences that once ran straight now zigzag across yards, pushed out of line by earth that won't stand still. Residents wake to find gates jammed shut, retaining walls buckled, and driveways split by fresh cracks. Utility crews work around the clock, repairing water mains and gas lines that shear apart as the hillside lurches forward. Power outages come without warning, not from storms, but from the slow, relentless movement of the land itself. For those who live here, the signs of change are everywhere. Mailboxes lean at odd angles. Steps to front doors sink or rise by inches in a single week. Some families keep a ruler by the window to measure how far the wall has shifted since last month. In 2024, satellite radar and ground sensors recorded the hillside advancing as much as 16 inches in a single month, a pace that leaves even longtime residents unsettled. The psychological toll is hard to measure. Some neighbors swap stories about sleepless nights, listening for the faint groan of shifting foundations. Others have learned to laugh about the daily surprises, finding a fence post pushed 2 feet into a neighbor's yard overnight, or a garden path that now climbs like a ski slope. But beneath the humor, anxiety runs deep. Insurance is nearly impossible to find. Property values tumble. The question of when, not if, a home will need to be abandoned hangs over every conversation. Living on this moving mountain means adapting to uncertainty. The ground is always in motion, and so are the lives built upon it. Every new crack, every failed pipe is a reminder that nature, not city plans or engineering, sets the rules here. The numbers behind the rising seafloor are as clear as the cracks zigzagging through Rancho Palos Verdes. When geologists measure the movement, they use a straightforward formula. The amount of vertical uplift, U sub v, is equal to the horizontal slip, U sub h, multiplied by the tangent of the ramp's angle. Written as U sub v is approximately U sub h times tan alpha. This isn't just an equation on paper. It governs every inch the land shifts. If the ramp beneath the slide tilts at 6 degrees, each meter of horizontal movement lifts the seafloor by about 10 centimeters. When the angle steepens to 12 or even 22 degrees, the same amount of slip can double or triple the vertical rise. Field surveys and satellite data confirm these calculations. During heavy rains, the ramp's geometry dictates exactly how much the ocean floor will bulge upward for every surge of the hillside. In some parts of the slide, where the ramp thickens or bends, uplift rates spike, matching model predictions almost perfectly. Laboratory experiments back this up. In controlled settings, blocks of earth on inclined planes move and lift in proportions set by the ramp's angle, just as the formula predicts. The sensitivity to ramp angle means even a small change in underground geometry can have dramatic effects at the surface. Engineers and city planners now monitor these numbers obsessively, knowing that the next spike in rainfall could translate into measurable new land offshore. The mechanics are simple, but the consequences are anything but. The uplift isn't random. It's a predictable response to the relentless geometry of the Earth, a process that plays out with every slip and every storm. City budgets tell a story that science alone cannot. Since the first signs of acceleration, Rancho Palos Verdes has poured nearly $48 million into the fight against the landslide. Year after year, council meetings have authorized new rounds of emergency spending, retaining walls, slope monitoring, utility repairs, and road rerouting. Every time the ground shifted, another contract was signed, another engineering firm brought in, another round of repairs begun. But the land kept moving, undeterred by money or manpower. The city manager, pressed by reporters and residents alike, has described the effort as a race against nature with no clear finish line. In council minutes from 2023 and 2024, officials debated how long they could keep patching roads and pipes before the budget simply gave out. The costs have not just drained city coffers, they've forced hard choices about what can be saved and what must be surrendered. Utility crews have replaced the same water main 3 times in a single year. Retaining walls built for millions have lasted months before splitting apart. Each new failure comes with a price tag, and the totals keep climbing. By early 2024, the financial reality had become impossible to ignore. Federal disaster aid and state emergency funds arrived, but even these could not keep pace with the mounting bills. In March, a $42 million property buyout program was announced, offering at-risk homeowners the chance to leave before the ground claimed their houses for good. The fund, backed by federal and local dollars, promised market value offers, but came with a catch. Once bought, the land could never be redeveloped. For many, it was the only option left. The city's spending is now tracked in public records and council packets, every dollar debated in open session. But the gap between the scale of the disaster and the resources available grows wider each month. Engineers and planners have stopped talking about solutions and started talking about survival, about how to retreat safely, how to compensate those who lose everything, and how to prepare for what comes next. The numbers are staggering, but the limits of human control are even clearer. No matter how much is spent, the ground keeps moving and the sea keeps rising. A new layer of danger came into focus in 2024 when satellite interferometry and deep drilling revealed the landslide's true scale. INSAR analysts tracking ground movement from orbit noticed anomalies that didn't match the known shallow slip plane. Instead of a single sliding surface, the data showed entire neighborhoods shifting in patterns too broad and too fast to explain with the upper ramp alone. The ground wasn't just creeping, it was accelerating, and the movement reached farther inland and deeper underground than anyone expected. To find the source, drilling crews bored through hundreds of feet of unstable earth. Beneath the familiar bentonite layer, the drill bit punched into a second, deeper slip plane, hidden for millennia at depths between 245 and 345 feet. The core samples told a story of sheared shale and pressurized groundwater, a buried fault line lubricated by water forced down from above. In some spots, the deep plane was moving up to 13 inches a week, doubling the pace of the overlying slide. The deeper the drill went, the more evidence piled up. High pore pressures, fractured rock, and a bowl-shaped geometry that extended well beyond the boundaries of the original slide. The drilling engineer reviewing the borehole logs described the system as a bowl within a bowl, a stacked landslide complex with each layer capable of independent movement. The deeper plane's reach dwarfed the shallow slide, threatening not just homes and roads, but the very stability of the peninsula. INSAR maps lit up with hotspots, showing ground displacement over 700 acres, nearly twice what had been monitored before. Every rainfall sent pulses of water down to the deep slip zone, recharging the pressure and triggering new surges. The realization hit hard. The landslide was not a single problem, but a multi-layered machine, powered by forces far beyond the reach of surface repairs. The deeper plane had awakened, and with movement rates this high, traditional mitigation was no longer enough. The ground itself had become an unstoppable force, its full power only now coming into view. In 1956, a single road project triggered the reactivation of a landslide that had been dormant for 5,000 years, destroying over 130 homes in Rancho Palos Verdes. Scientific investigations revealed a hidden layer of bentonite clay with a friction angle of just 6 degrees, turning solid ground into a slow-moving slip zone. By 2024, parts of the hillside were sliding at a rate of 4.5 feet per month, while deep drilling confirmed a second slip plane moving nearly 13 inches per week at depths of up to 345 feet. Despite $48 million spent on mitigation and a $42 million federal buyout fund, no engineering solution has stopped the movement. The exact long-term behavior of the deeper slip plane remains uncertain, as does the ultimate impact on California's coastline. What is clear from decades of records and satellite data is that human actions, natural forces, and hidden geology combine to reshape land and sea. The story of the rising seafloor is not just a scientific mystery, it's a documented reminder that California's coast remains in constant, unstoppable motion.